Okay, so this chapter, chapter 4, is all about exponential functions. And really, we're talking about a growth curve and a decay curve are your main ones. And your parent curves are generally going to be this. 2 to the power of x, which is a growth curve, which just means as x increases, I take more and more exponents of 2. When you think about it, when x is 1, y is equal to 2. When x is 2, y is equal to 2 times 2. When x is 3, y is equal to 2 times 2 times 2. And as x increases by 1, we simply multiply it by 2 each time. If you were to look at the table of contents of this, you'll discover a very, let's just ignore negative for now. You'll notice this pattern, 1 to 2, 2 to 4, 4 to 8, 8 to 16. Each thing is doubling. 2 is multiplied by 2 to get to 4, 4 is multiplied by 2 to get to 8. In other words, it's multiplying by its base. So if you ever want to determine if a graph or a data sheet like this is a growth curve, take one number and divide it by the previous number. Take that number, divide it by the previous number. If the numbers repeat, for instance, 16 divided by 8 is 2, 8 divided by 4 is 2, 4 divided by 2 is 2, then you discover it's a growth curve because you found a ratio. You'll also use this in geometric series or sequences. And the 2 not only repeats, but that also tells you the base, and that's the base there. Whenever the base is above 1, whether it's negative or below 1, negative 1, ignore the negatives for now. Whenever the base is above 1, we have a growth curve. When it's between 0 and 1, we have a decay curve. Here's a decay curve, and here's the standard parent graph decay curve. It's a half to the exponent of x. And notice there's this nice symmetry. That's because this is sort of doing the exact opposite of that. As a matter of fact, we'll find identical points on either side of the, I can't quite hit it when I want to here. We'll find identical points on either side of the y-axis. It's kind of reflected in the y-axis. And that's because really this is very similar to 2 to the exponent of x. It's just reciprocated. So everything's going to get flipped. Or if I took all these values here and took the reciprocal of them, that's what I would get in this table. Let's test that theory. So if I take the same numbers, 0, 1, 2, 3, 4, 5. Is there 5 on that one? No, just 4. You'll discover that this number here is the reciprocal of that. This number here is the reciprocal of that. This number here is the reciprocal of that. That's all that's happening, which makes sense because all the base does is the reciprocal. But my point is, anything between 0 and 1 will be a decay curve. It'll start off high and slowly go down and try to reach the x-axis. Now that's another point. The domain and the range of growth and decay curves, the domain is always xer. But the range is y is bigger than 0. And that's because there's no value I can put for x in here or in here that could possibly result in a 0. There's no value of x I can put up here where the result will be 0 or negative. And therefore, my y values will never get to 0. Now, in this case, the bigger the x, the more huge my y value becomes, which explains why this red line goes shooting off to infinity. And in this case, the bigger the x, the smaller my y value becomes, which explains why it's trying to get to 0, but never quite gets there. Notice that they both try to hug the x-axis, but no, it looks like it's touching, but if we zoom in, we'll always discover a space. It's for eternity trying to reach the x-axis, but not getting there. These are the two main curves that you should take, and really if I'm going to focus on 2 points, and only 2 points, then the 2 points you should focus on are, let me just get rid of these, there we go, 0 for x and 1 for x, and here's why. You're always going to find a 0, 1 no matter what the base is. So if I take a 3, you discover 0, 1. If I take a 4 or 7, doesn't matter what I take, 0, 1. And that's because when x is a power of 0 here, the result is always, anything to the 0 is always 1. The other number you're always going to consistently have is 1, whatever the base is, which makes sense because 2 to the power of 1 is 2. If I change that base, it's going to become 1, 3. If I change it to 7, that's going to become 1, 7. So those 2 points, turning off the black line, make for a very easy way to remember the graphing points. And yeah, you can grab some extra points if your teacher wants it, but these 2 points are enough to essentially transform any graph. Now the good news is transformations work for one function to the next function. It's why they teach them to you, so that you can just learn how to transform any graph. So you'd really want to study the domain, the range, and at least 2 points. And if I'm going to take another point, it's maybe -1, and you'll discover that over here. But even then, it's not that important, or 2, which is 4 up here. And if really you know just the first 2 points, you can transform this graph. The same with this one, except for this one, you'll notice the points are kind of hard to remember on this side. So let's focus on the points I'm talking about. When it's 0, just like the growth curve, it's always 0, 1, and 1, the base. No matter what I make the base, that's the equivalent to 1/8 there in decimal. It's always going to be 1, the base, which means I have a very nice 2 points to always translate with. But the 2 main functions you're going to sort of have to memorize is 1/2 to the x and 2 to the x. Those are the 2 parent functions. This is the growth curve parent function, and this is the decay curve. And eventually you're going to move on to another one next year, especially called e to the x, which is still a growth curve. E is like a number like pi. It's a magical number, 2.71. I forget the rest of it. And it's related to finance mostly. But it's also growth curve. But the ones we're going to be working with are 2 to the x and 1/2 to the x. Memorize the domain and memorize those 2 key points that I think are the easiest ones to remember, which is 0, 1, and 1, the base. Then realize that all transformations take place. Now sometimes you might have trouble spotting what the base is. And for instance, if I have this massively transformed here thing, I get -2, 3 to the x plus 5, and your teacher asks you what the base plus 7, asks you what the base is, always focus on the x, which number the x is over. In other words, you can get rid of all the numbers around it, and even the transformations of x, and realize, okay, that 3 is above 1, so this is a growth curve, and the base is 3. I also want you to get into the notion that if I have y, let's take 5 to the x, right? And I take a table of contents of it, and I just go from, let's take 0, 1, 2, 3, 4, and I just quickly have a quick study of those. When you take the first differences of this, which means you're taking one term and subtracting the term before it, you see that this one here, okay, it goes up by 4, this one goes up by 21, this one's going up by 100, this one's going up by 500, and then when I take the second differences, I discover, okay, well, this one's going up by, it looks like it's going up by 417, and then 69, and then 400, and then as I keep going, these numbers never seem to get anywhere. And that's a hint that you should instead take this number and divide it by the previous number, just to see. So I take 5 and divide it by 1, that's 5. I take 25 and divide it by 5, that's 5. I take 125 and divide it by 25, that's 5. 625 divided by 125, 5. So when I take the division and I get the same number, it's immediately clear, especially since that's number above 1, that I'm dealing with an exponential function. And later on, you're also going to learn that this rule applies to geometric functions, which are really tailored down exponential functions. But remember that geometric functions follow this rule too. And not only that, but this 5 also told me the base. The base is 5. It's very clear when there's no transformations. It gets a little stickier when I add a simple transformation, like a simple y transformation, like adding 1, because these numbers are no longer do appear to be multiples of 5. But you'll still get a little hint if you suspect it's an exponential growth. You can take this number and divide it by the previous number. So I get 3. And this number divided by the previous number, and I don't know that off by heart, but you get 4.33. Let's just keep going and take a few more. The next number, 1, is more telling, and we discover the big numbers are more telling because the big numbers get rid of that slight diffusion. 4.84. And this one's even more telling. 626 divided by 126. And that's because as I take bigger and bigger x values, 4.96. And as I get closer, it's going to be like 4.99 and 4.999. And that's because in this stage, that plus 1 really distorts these low numbers. But in this stage, that plus 1 barely distorts these numbers, and you get a clear idea. If I were to keep taking the second differences on the big numbers, for instance, if I took a really big number over here, and took like, let's focus on 5, 6, 7, 8, 9. If you, let's skip the 9 because it's just too big, but if you take this 15,626 and divide it by the previous y value, 3,126, you will discover it is very close to 5, 4.99. If I take that very last one, 390, 626, and I divide it by the previous one, 78126, I discover like 4.99999. And it's very clear that as I go up here, I can say, okay, you know what? It looks like these are actually, it looks like this is going to be a 5. So I have a sneaking suspicion there's a 5 as the base. And then I just got to figure out, okay, 5 to the 0 would be 1, but I have 2. 5 to the 1 would be 5, but I have 6. 5 to the 2 would be 25, but I have 26. And immediately you can say, well, it looks like it's just one more, one more, one more. 5 to the 3 is 125, one more. And you can quickly say, I think this is the rule. Another way to do it, which is more sound mathematically, is to take your base formula. And your base formula is this. Y is equal to the base, and you know it's growing because the numbers are getting bigger, to the power of x, and we'll forget all the x transformations. And actually, let's do it totally complete. There might be an a in here, a b to the power of x, and a plus c. And we don't know the plus c or the a. We have a sneaking suspicion already that the base is 5. So we're going to work with that assumption that the base is 5. And we can put in a couple numbers. Let's leave a alone for now. And just, you'll see how it can work. We'll get more and more advanced. And I'm just going to work with this one. Well, if I replace that, I get 2. I get 5 to the 0, and I get c. And 5 to the 0 is clearly 1. So I get 2 is equal to 1 plus c. It looks like c is equal to 1. And if I do the next one, I get the same idea. Well, that's easy when there's just a c. But now let's add another transformation there. Let's make that 2 times 5. We're going to just make it 0, 1, 2, 3. Notice suddenly I get this jumping up. But if I do the division still, I discover, oh, it looks like a base of 5. I just don't know that 2 or that plus 1. Well, you can still use a little bit of algebra to get close or get an idea. This is where first and second differences are really useful. If I look at this formula, b to the power of x plus c, and I just work on this basic premise, and I do the first one, well, I get y of 3 is equal to a mysterious a 5, which I think I'm working with. The x I'm using is 0, plus c. Well, it's clear that 5 is 1, so I get 3 is equal to a plus c, which means a is equal to 3 minus, or c, it doesn't matter. A is equal to 3 minus c. Well, let's put that aside. And this is mathematically sound. This is without a doubt and accurate, as long as the base is 5. And then if I go to the next number and I replace my y value with 11, and I do the same thing, I get 5 to the value of what is x going to be? It's going to be c, and plus c. Suddenly I get 11 is equal to 5a plus c. But up above, I can see that a is equal, and actually let's make it easier. Let's use the other version of that, which is also that c is also equal to 3 minus a. So let's replace this with 11 is equal to 5a plus what I know c to be equal to in the first case. When I do that like that, I get 3 minus a, which is clearly 11 is equal to 4a plus 3. And then I get 4a is equal to 8. Therefore, a is equal to 2. Suddenly I've discovered, now I can go back here, and I can say, okay, well, my c is equal to 3 minus a, which is 2. So my c is equal to 1. So suddenly I've discovered that a is 1, a is 2, c is 1, and I only had to do a couple of numbers. Now, it gets more complicated as there's more transformations. However, this method, as long as you have enough numbers in the sequence, you can figure out your curves. That's why first and second differences is a really good technique to learn. Now that we studied the basics of exponents, they want you to go through your exponential rules. So I can't stress this enough how much you're going to need this in other courses as well. But I strongly urge you to study your exponential rules. Okay? And especially this one confuses a lot of students. When it's a fraction, the bottom portion just means a root of some kind. In this case, a square root. If that was a third, 1 over 3, that would be a cube root. There it does right there. And then they put it in a generic form like this. Now, they always give an example over here of how to figure it out. Really, you should start with these ones. So the rule is that it has to be the same base, and you can add their exponents. When the same bases are multiplying with an exponent, you can simply add their exponent. This will especially come in useful for solving certain puzzles. When you have the same base with an exponent divided by the same base with an exponent, you can just take the same base and subtract their exponents. This is done easily through experimentation as well. So if I have 3 to the 3, and it's over 3 to the 1, this thing's telling me it's 3 to the 3 minus 1, which is 2, which is 9. But I can also see, if I do it the long route, 3 to the power 3 is 27, divided by 3 is also equal to 9. The problem with this route is you can be dealing with so many multiplications, it's easier to just start figuring out a method to make it easier. And that's all of math, a method to make it easier. In this rule, an exponent of the exponent, you take the same base and you just multiply those exponents. And they always give an example. And then when they're different bases but the same exponent, you can rewrite them in a bracket with the exponent outside. So that's an unusual situation. This is a really important one. Anything to the 0 is equal to 1. And this is also a really important one which throws students. A negative exponent just means if it's in the numerator, it now goes to the denominator with that same exponent but positive. And the same is true as if it's in the denominator. If I'm doing 1 over 8 to the minus 1, the 8 goes to the numerator, and it's 8 to the power of 1, which is simply 8. So 1 over 8 to the negative 1 is simply 8. But the rule is, if I'm dealing with x to the negative 3, right now this is technically in the numerator, so that negative 3 simply means it's 1 over x to the power of positive 3. So the exponent changes signs, and I put the x in the opposite area of the fraction. Super important because it's going to apply to a whole bunch of different courses. So they want you to go through and revisit all your exponent rules and how to add fractions, how to divide fractions, how to work out first differences, second differences, and it's pretty useful. And then they get you to explore a little bit of decay. So very often the types of decay we're going to be dealing with are things like oh geez, what's a good decay? Well, acceleration based on velocity I think would be a good decay. Let's see, no, that won't be a decay. It'll be an inverted growth. But more common you'll see for growth, population, virus spread, bacterial spread, finances, so compound interest, so population growth. So 2 people have 4 kids. Those 4 kids 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 have 4 kids. You can see how quickly, after 5 generations, we've gone from 2 people, 7 generations, to 2 people to 1,024. but these big numbers will really grow. So population growth, bacterial growth, bacteria and viruses grow much faster than humans. And then you also see compound interest, which means if I give you $100 and I give you 10% at the end of the year, you'll have 110. But if you take that 110 and you put it into the bank and I give you 10% again, you'll have 121. If you take that 121 and put it in the bank again at 10%, you'll have 133.1, something like that. And you can see these numbers aren't going up by 10 each time, but they're actually growing. And the secret is just to look at sort of the tens. You can see them going up by a certain percentage. And compound interest follows that. So it's important to learn that. Now decays look like that. Certain things that do decay is radioactivity. Radioactivity has a half-life that's millions of years, but let's put it in simple terms. If I have 1,000 grams of a radioactive material and it decays to half its mass in 7 years, what will happen after 7 years? It'll be 500 grams. What will happen after? So it'll be 500 grams in 7 years. What will happen 7 years later? It'll be 250 grams. What will happen 7 years later? It'll be, no, that should be 14. It'll be 125. And it'll keep shrinking like that. And that's done like this. So the half-life, we know it's a half-life. So we would start with a half. We know we're starting with 1,000 grams. So we put a multiply of 1,000. And let's see. That should not be a growth curve. There we go. And then because it is happening every 7 years, we have to take our x and multiply it, I think, by, is it 1 over 7? I think, no, it's actually multiplied by 7. And so I'll put it in brackets. There we go. And now I'm just going to pull up a table to see if I got it right. So what happens after year 0? We got 1,000 grams. Year 1? No, I did it slightly wrong. So I think it would have to be, is it 1 over 7? Might be 1 over 7. No, I think what's happening here is it's not quite getting my multiplier correct. So I got 1 is equal to 1,000. And it'll help if I put it all in brackets. That might help. So let's see. No, I still don't quite have it right. So I sort of failed in coming up with a good analogy of what happens after 7 years. I think it has to be in brackets x over 7. Does that work? Let's see. We'll go to 7 years. Let's put in 7. Yeah, there it is. My bad. 7, 14, 21, 28. So, to express this better, why isn't it? Oh, I hate when it doesn't. Let's put it here. There we go. To express this better, to get an idea, see when x is 7, it divides by this 7 and it becomes an exponent of 1, which is the only time this half becomes a half and then multiplies 1,000, which explains why every 7x units this amount decreases. That's a lot to absorb, but it's the idea here is accurate. This thing is, and whatever, if it decays in 14 years up here, I just put a 14 in. If it half-lifes in 14 years, and then I can see, okay, 28, 42, and then 50, 70. You can see that this is now going down in half a mass every 14 years. So a lot of half-lives will always start with a half base. Now also notice this formula looks pretty complicated, but the secret is to say, okay, where's the exponent? There's the x. So that's the base. And all you do is strip away everything affecting the x to see that's the basic growth curve you're working with. So if you know the main points of this curve, you can come up with the main points in this curve through transformation. And what are the transformations that are going on here? Well, there's a couple of x. There's an x transformation. It's stretched by a factor of 4. And there's a y transformation. It's stretched by a factor of 1,000. So I multiply all my, so the first point was 0, 1, so I multiply it by 1,000, and I multiply that by 14. And then this one normally is 1 comma the base, which is 1 comma a half, but I multiply the y value by 1,000, I get 500. And I multiply the 1 by the 14 stretch up here. Just remember, it's the opposite. This is like 1 over 14 as a multiplier to my x. And it's always the reciprocal. It's the opposite of what you expect for the x transformations. So essentially, I just multiply all my x values by 14 and all my y values by 1,000 on the original transformation of the original parent graph of the decay curve of a half. Anyway, radioactive material, things that depreciate, buying an automobile. So every year, an automobile loses, what is it, 20% of its value, something like that, 15% of its value. So that means if you buy a $10,000 or $10,000 car this year, let's say it loses 15% of its value. Next year, that car, if you don't bang it up and ignoring mileage, let's just say it sits in your driveway, that car will be worth $9,850. And then it's going to lose 15% of that. So in this case, if this is the initial amount of the car, and you might say, well, how is 15% represented in a decay curve? Well, it's the decay of 15 over 100. So if I look at, say it's every year, I can use this as the root and put it to the power of x and multiply it by 1,000. Let's see if that works, or 10,000. So if I have a car that's worth 10,000 and it depreciates down to 15%, so what's 15% off of 100? 85 over 100. Sorry if I said it was 15. And it's going to be to the exponent of x. So it's going to be 85 over 100, all to the exponent of x. So you can see in the first year, oh, and I have to go 1. Yeah, 1, 2, 3, 4. You can see in the first year my car's 10,000, but after 1 year my car has gone down in value. And let's see, oh, I had it even, it's even worse. It's down to this value, and the next year it's down to this value, and down to this value, and then to this value. And I'd have to go way up on 10,000, so I'd have to change my y-axis to 10,000 to see it properly. There we go. That's when I first buy my car. That's after a year. That's after 2 years. That's after 3 years. That's after 4. So we can see my car is getting worse and worse in value as time goes on, as soon as you buy it, actually. The other thing is annuities are going to be counted this way, and I forget what else, but there's a few decays. But they like to put it in real-world situations. So that's going to be explaining that. You also have to get used to the powers of 12 and what they mean. So the easiest thing to know this is how many zeros in that? There's 6 zeros. So that's 10 to the power of 6. In this one, how many zeros after the decimal? There are 4 zeros. So that's 10 to the negative 4. And so the idea is a negative exponent if you're starting with 10 to the negative 4, right? So 10 to the 1 would be that. 10 to the 0 is 1, right? So 10 to the negative 1 is 0.1. 10 to the negative 2 is 0.01. 10 to the negative 3 is 0.001. And 10 to the negative 4 is 0.001. So that's how you think of it logically. Negatives are moving the decimal this way, and positive increases are moving the decimal this way. So obviously when you're dealing with things like atoms, you don't want to put down 1,000,000 atoms. You're going to say, okay, I have 8.32 atoms times 10 to the power of 9, which means 8.32 billion atoms. Because 10 to the power of 6 is 1,000,000, so 10 to the power of 9 is 1 billion. And you're going to write it like this. And earthquakes work like this as well. An earthquake magnitude of 9 is they just focus on this. An 8, they focus on that. So earthquake magnitudes, when they say it was a magnitude 9, a 9 is 10 times more powerful than an 8, not 1. An earth magnitude 5 compared to a 9 is how many? There's 4, so it's 4 zeros. So it's 1,000. Actually, no, that's 3 zeros, 10,000. A 9 is 10,000 more powerful than an earthquake of magnitude 5. And this is called a log value, which we'll get into. Logs are sort of the reciprocal, the inverse function of an exponent. And they just want you to get used to powers and how to resolve things like negative powers. And then they put you through the main rules. And a lot of these textbooks, you can just jump to the main rule. If you get the main rule, go ahead and start the questions. Now, some of these are common sense, so I'm not going to spend too much time on them. You want to study your exponent laws. So what is a negative 1? It's simply 1 over 5 to the power 4. This was a numerator, so it now goes to the denominator with a positive, the same number, positive 4. And that's like 625. So the answer is something like 1 over 625. Now, I'm not going to waste time doing the calculator expansion of this. You can do this step, but I'm just showing you what the negative means. Also, the nice thing when it's outside of the fraction like this is you can just flip the fraction. So the minus 3 just means I can flip this fraction, 10 over 1, and change the negative to a positive. That's the fast way. And then you've got negative 10 to the power 3. So any negative number that's to an odd power will stay negative. So 10 to the power 3 is 3 zeros. So the answer to this is negative 1,000. But there are several ways you could go about it. So another rule of this is this negative 3 could also be applied individually. You can get rid of the brackets and apply individually to each thing, like this, and then flip them individually. I really don't see a point in that. When you have a nice fraction like this, it's just easier to flip the fraction, change the sign. Now this negative sticks around. Flipping the fraction does not change this to positive. It just changes the exponent to positive. So this one, you can see the number is in the denominator, like that. So all that it means is this now goes to the numerator and becomes a 4. Now, had there been something like a 2 up here instead of a 1, had there been something like a 2, or let's say a 3, then it means the 2, since the 3 was being divided by the 2, the 3 is now multiplying the 2, which is to the positive 4. And 2 to the positive 4 is 4, 8, 16. So the answer to the question they're asking is just 16. But if there was a 3 there as a numerator, I would then multiply this by 3 and the answer would be 48. That's just in case the numerator is not always 1. Essentially, it was dividing, it's now multiplying. And like I said this time, the tricky thing about this one, though, is they put the negative on the outside. So the rule of BEDMAS says I have to do exponents first. And this is essentially a minus 1 multiplying this. So this is an exponent first. As I said before, the simplest way is to bring this 5 to the numerator and this 6 to the denominator, like so. I kind of ruined the fraction, but whatever. And then change this to a positive. And again, I still apply the exponent. So 5 to the third and 6 to the third. So that's another rule of the exponent. This essentially can be applied to both things individually. 5 to the third, I think, is, I forget what it is. It's like 125. And 6 to the third is 36 times 6, which I don't know. 180. And 36, 180, 216, I think. And then finally, now that I've resolved the exponent, this minus is multiplying this fraction. So it's essentially BEDMAS order. This one, as I said before, they're actually very easy when you do it this way instead. The 11 can just go up to the numerator, and the 3 can come up to the denominator, and we change that negative 1 to a positive 1, And of course, since that's just 1, it's 11 over 3. And I sometimes erase the fractions, but it's still there, like that. And this one is the same thing, except that you'll say, well, they have different exponents. That's okay, because the exponents don't apply to anything other than the numbers they're attached to. It still switches places because they're both negative exponents. And after I switch places, I change it to a positive. So it becomes 8 to the power of 1 is just 8, and 7 to the power of 2 is 49. So the ultimate answer is 8 over 49. That's how they all work, like that. You just got to follow bedmass order and exponent rules. Now, when things have the same base, that's the only time you can add their exponents. These are indeed both minus 10s. So if they're multiplying like this is the same base times the same base, so I'm allowed to add their exponents. What's plus 8 plus minus 8? It's the same as 8 minus 8, which is becomes minus 10 to the 0. Now anything, doesn't matter what it is, to the power of 0 is simply 1. So the answer to this is 1. These have the same base. That's the first question you always have to answer, which means if I'm multiplying them, I can add up the base. Minus 7 plus 5 is minus 2. 6 to the minus 2 is what? 6 to the minus 2 is what that final answer is. The rule for a negative, it now becomes 1 over 6 to the 2, which is 1 over 6 to the 2, which is 1 over 36. Very good. There we go. Like that. And sometimes I'm just going to skip. As we go here, I'm just going to go over the rule. Okay, are these the same base? Yes, they're being divided, which means I have 8, whatever this exponent is, minus this exponent. Don't mix up the numbers. It's always top exponent minus bottom exponent. And if you have to, put the bottom exponent in brackets to keep it clear. What's the bottom exponent? It's minus 5. What's the top exponent? 8. What's 8 minus minus 5? It's 8 plus 5. And that's 13, which means this comes out to 2 to the power 13. And if your teacher wants you to expand that, you have to put it in your calculator. Do these have the same base? Yes, they do. So it's the same rule. What's the top exponent? Minus 3. What's the bottom exponent? Because it's positive, I don't have to worry about that bracket so much. It's minus positive 5, which is the same as minus 5. Minus 3 minus 5 is minus 8. So I end up with an 11 minus 8 up at the top. So that means that is 1 over 11 to the power of 8. So it's 1 over 11 because it now goes to the denominator because of that negative number. And then you just take 11 to the power of 8 in your calculator to figure out what that comes to, and that's 1 over whatever that number is. What's an exponent? What's the exponent of an exponent rule? The exponent of the exponent rule is you can just multiply the exponents. So what's 4 times minus 1? It's minus 4. So you get not minus 9 to the minus 4. What's the rule for that? It becomes 1 over 9 to the positive 4. And then you just find out what that is, and it's 1 over whatever that is. Here you can even have triple exponents. Yeah, triple exponents are... oh, it doesn't matter. These aren't triples. I don't know why I put the other bracket out here. Maybe there was a number that I accidentally erased. But what's minus 3 times minus 2? It's 6. So it's 7 to the 6. Which means you just put in your calculator to figure out what that is. I'm just going to make sure I didn't cut off anything. Oh, yeah, it has a minus 2 out there. So there's actually another, that's where the brackets were out there. There's another minus 2. So what do you, so it's not 6. So what do you do? It's minus 3 times minus 2, that's plus 6. Then times minus 2, minus 12. So it's 7 to the minus 12. But you're not done. That's the same as 1 over 7 to the 12th. Then you just put in whatever 7 to the 12th is, and you put 1 over whatever that is. 3 is actually more straightforward when you apply the negative rule, and it should be intuitive. So let's look at this one. This rule here is I can just take the fraction. They're asking which number is bigger. Well, I can just take the fraction and switch spots, which means I have 2 over 1. I'm not going to even bother with the 1, and I just change that to a positive 5. 2 to the power of 5 is 4, 8, 16, 32. 32. Now we're going to compare it to this one. And I can tell you anything like this number that I'm about to do is going to be smaller because it's going to be 1 over 2 to the power of 5, which is the same as we just discovered 2 to the power of 5 is 32. So it's 1 over 32. And it's quite clear that 1 over 32 is smaller than 32. And they just want you to practice understanding why it's different. A lot of these are pointless, so I'm going to just go through the rules because this is kind of like grade 10 stuff, really. So I'm just going to get rid of that. There we go. So what's the rule here? Are they the same base? Yes, they are. So add their exponents. It's going to be 2 to the power of 4. You can figure that out. What's the rule here? Are they same base? Yes. So it's 4 minus 6. So it's 5 to the minus 2, which is 1 over 5 to the 2, which is 1 over 25. So that's done. What's the rule here? You multiply their exponents. So it's 4 to the power of 3, and whatever that is, that's what you would do. And when it says rational form, it means you have to expand it. What's same base? Yes. So what's 3 plus minus 3? 0. What's minus 8 to the 0? It's 1. Minus 8 minus 6. So that's minus 8 plus 6, which is 3 to the minus 2, which is the same as 1 over 3 to the 2, which is 1 over 9. Multiply this. It's 7 to the power of minus 2, which becomes 1 over 7 to the positive 2, which becomes 1 over 49. Same base? Yes. So the easiest thing here is first multiply these. So I got minus 2. Then minus 2. I got 3 plus minus 2 because the rule here is you add them. The rule here is I multiply them here, but the rule here is I would add whatever the result is. But because I have an exponent of an exponent, I have to resolve this first. So this becomes 3 to the minus 2. And then 3 plus minus 2 is 3 to the 1. So the answer is simply 3. Again, with this one, I have to expand it first. I get minus 3, and the rule is top minus the bottom. So minus 3 in the top, minus minus 3, which is minus 3 plus 3, which is 12 to the 0. So the answer to this is 1. Here I have to expand this. They're just making you do it in the right order first. It becomes 5 to the minus 6. It becomes minus 6 minus minus 6, which is minus 6 plus 6, which is 5 to the 0, which is 1. Here, what's interesting about this is because these are in the bracket and this minus 2 is outside, I should resolve inside the bracket first. So it's bedmass still. Brackets first. Minus 2 plus 3 becomes 3 to the 1. And 3 to the minus 2, even though it's 3 to the 1, it's still just 3 to the minus 2, becomes 1 over 3 to the 2, which is 1 over 9. So it's just following the correct rules in the correct order. So here we're dealing with a bracket first. There's another option too. You can apply this minus 2 to each of them individually, like that and that, if you wanted to. But I actually find doing it in bracket order is going to be a lot easier. So if I look at the bracket order, this is essentially to the power of 1. What's 1 plus minus 1? It's 9 to the 0. So it's 1 to the minus 2, and no matter what, 1 is put to the power of 2. It's going to be 1. Here I have to expand this first. I get 5 minus to the minus 6. We did that one, I think. It's minus 6 minus minus 6 is 0. And we did that one too. Or at least you should know how to do it by now. Let's see. 6, 7, 8. They're all pretty much the same. They just want you to follow the same rules. They just want you to be comfortable with the rules. Okay, so what's going on here? Well, you got to look at it carefully, and you'll immediately see that this bracket here surrounds these two numbers. So that means I have to resolve them first, so they're the same base, so I add them. 4 plus minus 2, which becomes 10 to the 2. So this whole thing inside the bracket becomes 10 to the positive 2. Then this one outside is 1. So 10 to the power of 1 times 10 to the power of 2, I add them, becomes 10 to the 3. What about this one? Well, because there's no brackets separating one from the other, you can just add up all their exponents because they're the same base. So this is a 1 here. 1 plus 2 is 3, plus minus 4 is minus 4, so it's minus 1, so it's 8 to the minus 1, which is the same as 1 over 8. And actually, sometimes scientists like to express it this way because it keeps it all on the denominator and keeps fractions out of it. What about this one? Well, we have an exponent of an exponent in the bottom, so you should resolve that first. So down below it becomes 6 to the negative 4. And then it becomes negative 5 up top minus 4, which is minus 1. So it becomes 6 to the minus 1, which is the same as 1 over 6. So they're all like that. So here, when you get in these complicated ones like this, just do the brackets first. It helps if you just have a plan. So the brackets here is, we'd follow the rule minus 5 minus 6. So it becomes 2 to the minus 11. Now there's no need to put it into the fractionary form yet because we're now multiplying it times 2 to the 8. So we add these. 8 plus minus 11 is 8 minus 11. It becomes 2 to the minus 3, which is the same as 1 over 8, or 2 to the 3. And it's the same thing here. You've got to multiply the bottom first. So you get minus 12 here. Minus 10 minus minus 12 becomes plus 2. So you get 4 to the 2, which is equal to 16. And here you got to do the brackets first. But the nice thing about the negative 1 is you can just swap the top and the bottom. And that just becomes 1. And 1 is just that. And so you can do 8 minus 2. 8 minus 2 becomes 13 to the 6. 13 to the 6. And I can just get rid of this bottom now. Now I can add these fractions. Minus 5 plus 6 is plus 1. The answer is 13 to the 1, or just 13. Okay. Oof. All right. So you might say, I don't get it. I can't do this one. Except that 16 is equal to 2 to the power of 4. Yeah, 4 squared 4. Which means I can replace this with this. Which means minus 1 times this 4 becomes minus 4. Now, you might say, can I add these? Because it's kind of weird. All of a sudden I'm adding these. Right? 2 minus to the minus 4 minus 2 to the minus 2. Well, you've got to resolve it a little bit better, because let's see, what can we do here? Let me see if I can resolve it a little bit better. Well, it's a minus, so you don't really have to resolve it at all, because it's really, what's 2 to the minus 4? It's 1 over 16, minus, what's 2 to the minus 2? It's 1 over 4. And so you have to multiply this by 4. You get 4 over 16. So the answer is minus 3 over 16. So they're just kind of doing this weird adding stuff, mixture. Let's see if there's any weird ones in here we can do that's easier. Minus 3 to the negative 1 is the same as negative 1 over 3. 4 to the 0 is 1, minus 1 over 6. So in order to put them all in the same fractions, I have to multiply this one by 2. I have to multiply this one by 6, and this one just stays the same. So that means they're all now going to be the same as being over 6. What's minus 2 plus 6? That's 4. Minus 1, 3. So it's 3 over 6, which is a half. Let's see if there's a tougher one in here. I'll do them all because these are all kind of weird. So what's the nice thing about negative fractions? You can just flip them. Notice they're minus, so you just leave the minus alone. So I'm going to bring that up there, and this is going to go up there. And I changed the -1 to a +1, or just nothing, really. And the same with this. This comes down. Ah, geez. And this goes up. So I get 5/2 to the 1. Now it's just a matter of adding fractions. Keep in mind this -3 is up there, and you can just think of the 2 as the whole thing is over 2. So what's -3 plus 5? Remember, it's a plus here. It's 2. So what's 2/2? It's 1. Okay, what's the nice thing about minus? You can just flip them. So really this is just 5 because it's 5 to the 1. And this one is -2/1, which will now be put to the power of 2. What's -2 squared? Keep in mind that negative doesn't go anywhere. What's -2 squared? It's 4. What's 5 plus 4? It's 9. Okay, I think I cut this one off a bit. I'm going to go look. No, it's just in brackets. What's 5 to the -3? It's 1/5 to the 3, which is 1/125. Plus 10 to the -3, which is 1/10 to the 3, which is 1/3 zeros. -8. -8 times what is essentially 1/1000. -8/1000. This has the same denominator as this. This needs to come up to speed. So I need to find a way of bringing this up to 1000. If I multiply it by 8, that works, because 8 times this will make 1000. So this becomes 8. And then it's all over 1000 now. 8 plus 1 minus 8, it's just 1/1000. And depending on what your teacher wants to express it as, that would be either 10 to the -3 or 1/1000. Okay, let's see if I can get rid of all that mess and do the last one. Okay, this is just a -1 here. And that's just a 3. Okay, let's do the 3 to the -2 first. That's simply 1/9 minus 1/36. This is to the -1, so it simply becomes -1/9 because that negative still sticks with it. It's multiplied by 3 at the top and 2 at the bottom, so 18. How do I turn this into 36? I have to multiply by 4. This is already fine. How do I turn this by 36? I have to multiply this by 2, so it's -6. So I get +4 minus 1 minus 6, so 4 minus 7. I get -3/36. Divide both by 3, I get -1/12. Whew. This one, I don't know if I'm going to do it or just tell you how to do it. So let's see. So what's the problem with this? So this -4 puts it to the bottom. The minus is going to disappear because that's going to become an even power. So it becomes 25 over 1 with 4 zeros. You can divide both by 25, and it becomes 1/400. So that's that answer. So it's just labor intensive. That's all they want on this. Whoops. Yeah, it's just labor intensive. What about this one? It's 1/16. And whatever 2 to the 5 is over 16. And I imagine they can probably both be divided by something. What is 2 to the 5? We might as well find out. Well, actually, you know what? Let's save ourselves some time because 16 can be expressed as 2 to the 4. That's what they want me to do. And I can subtract it. The answer is 2. And same with this. The nice thing about this is the minus 4 just comes up, minus 12 just comes down, and their negative exponents go away. And this just simplifies to minus 1 over 3. So they're just little tricks. So the easiest thing for this one, don't know if that'll work actually. First, let's expand that. That's 3 to the minus 2. And then we're going to, so that would essentially bring it up to 3 to the 2. And this one brings it down to the minus 9 down here to the power of 2. And so you're going to get slightly different. So minus 9 to the power of 2 is 81. And up top is 9. So you get 1 over 9. Okay, so these can all be expressed as powers of 2, which is what they're getting at here. 8 is 2 to the 3, which is 2 to the minus 1. So that becomes 2 to the minus 3. Then it's multiplied by 2 to the minus 3. So I can add them. Then it's divided by 2 to the 2 to the minus 1, which is 2 to the minus 2. So minus 3 plus minus 3 is minus 6. Minus 6 minus minus 2 becomes minus 6 plus 2. So it's 2 to the minus 4, which is the same as 1 over 16. And this last one's the same way. They want you to recognize that 25 can be expressed as, that's an interesting thing here though, because of the negative. Let's solve the 5s here first. Instead of swapping them, I can do 3 minus minus 2, which becomes 3 to the negative 5 to the power of 5. So that essentially gets rid of this. Now, I think what would be easier, now that won't work. I was going to do this to the square. I know there's sort of a way of doing, but the problem is minus 5 squared is not minus 25. I'd have to do minus and then 5 squared separately, and then I'm not allowed to apply that. So instead, let's bring it down to the bottom where it belongs. So it's like that. And I'm just going to accept that this is going to be, when it expands, is minus, and that this is minus. So I'm going to end up with a positive. So I'm just going to ignore my pluses and my minuses. And I'm going to accept that 25 down here is 5 to the 2. And then I'm going to subtract them. So the answer is 5 to the 3, or 125. Yeah, they're just making you stretch. There's nothing to that. I'm not going to bother. Oh, so they just want you to practice. You don't need me for that. This is essentially substituting wherever you see x for the number they're giving you, and wherever you see y for the number they're giving you, and wherever you see n for the number you're giving you. You have to add these first before you ever do it, and then resolve the exponent. I don't see a point in this. In this case, you can multiply the exponent. So if n is minus 1, you get x to the minus 2 here. But, that's just a rigmarole. So Kendra's noticing some mistakes. So let's see what Kendra's problem is. What's up, Kendra? Why are you looking at Eric's and Vin's homework? Go do your own homework, Kendra. So they're looking to evaluate this. Let's just see what it's supposed to be. So this is the same as 3 over 3 to the 2. 3 to the 1 over 3 to the 2 is the same as 1 over 3. So that should be the answer. Neither one of them gets it. So if you look at this, The problem here is, so she's adding it. So that's correct. But right there, there's a mysterious minus that appears. That doesn't even come into it. This part here is the correct version of that. So it's that minus that appears. And over here, that's incorrect because it's to the power of 1. So that should not be to the minus 2. That should be to the minus 1. That was another way to do it. I should have just added their exponents instead of doing that. Oh, no. You don't need me to do that. Don't need me to do that. Okay, let's look at 15 because it might be a little nuanced question that throws some students. The others are just pretty much what we just did, but with missing variables that you fill in, so I don't really see the point. So read that. Explain the difference between evaluating this negative, which is to an odd number, so it's going to come out negative, and evaluating that with a negative exponent. Well, they're totally different. So minus 10 to the negative to the 3 just becomes minus 1 with 3 zeros. Minus 1,000. This is the same as 1 over 1,000. They're not even similar. So it becomes 1 over 10 to the power of 3. This, because it has an even exponent, will come out positive. So it'll be 1 with 4 zeros. And this, because it would appear this negative is separate outside, this is including it in the exponent, so this implies that it's not, which means it's a minus 1 times 10 to the 4, which is also 10,000. However, with that minus 1, it becomes minus 10,000. So the difference is this negative is separate from the exponent, and this negative disappears because it's part of the exponent. So, okay, this is actually useful because before they teach you how to do logs, you have to solve these questions in this manner. You have to find an expression for 16 that is equal to 1 over 16. Well, that's 16 to the 1, but if it's going to be in the numerator, it's clear that this must be minus 1. So x is equal to minus 1. What number do I put to an exponent to always equal 1? It's 0. How am I going to get this to there? Well, let's break this down first of all. 25 is also 5 squared to the n, right? Which means 25 to the 2n. 5 to the 2n, if I'm going to put it down here, is 5. What makes 625? 5 times 5 times 5 times 5. So it's 5 to the 4. Now that means if this exponent is going to come down to the denominator, the n must be minus. It must be minus. In other words, let's rearrange this with a minus. This is the same as 5 to the minus 4. So now that I have two things where the base is the same, it must mean the exponents are the same, which means 2n must be equal to minus 4, which means n is equal to minus 2. If I go back, oh, it turns out 25 squared is also 625, so I didn't have to convert it to that. So if I go back to this one here, I can put in minus 2 for n, it works out. Because this is the same as 25 squared, which if I want it in the numerator is 25 to the negative 2, which means n must be negative 2. It's the same thing, and they're all like that. Okay, so let's try to express what 1 is in a fraction. 0.001. It's the same as 1 divided by, not 10, but 100. It's 1%. 0.001 is 1%. If I express 100 as an exponent of 10, it's 10 squared. If I wanted to put it into that numerator instead of where it is in the denominator, to move it up to the numerator, I would have to put a minus in front of it. For it to come up here, I have to put a minus in front of it. Now, I have a base equaling to the base, which means their exponents must be equal. So x is equal to minus 2. You can always go back and try it. Plug in x to the exponent of minus 2 to see if you get left side is equal to right side. So here I have to figure out what 2 becomes 1.25. Well, my knowledge of fractions tells me that 1 over 4 is 0.25. My knowledge of exponents tells me that 4 is 2 squared. My knowledge of the plus minus tells me if I want to bring it up to the denominator, I have to put it as 2 to the minus 2. Now that I have base equals base, their exponents must match. A lot of n's minus 2 here. This one's no difference. What's 144 as a 12? It's 12 squared. What do I have to do to bring it up to the denominator? I have to make it a negative exponent. I'm even going to borrow this. Since base is equal to base, n must be minus 2 again. There was a little pattern going on. Oof, 17. Oh, we're in the extension. Well, these are important, actually. That means we're almost done. We're in the extension. Okay. 17's, these are worth doing because you will be doing stuff like this in the next level. So ask yourself, how am I going to make these equal? And it's a little tricky here. And let's see if I can do it. What number, how could I express, let me see if I can do it here. 10 to the 2y is equal to 25. So it's very hard to make their bases match, right? Do 10 and 5 have anything in common? Yeah, they got a 5, but not as roots. So I'd have to ask myself, how is that going to ever be possible? And you know, I'm just kind of, I used to know instantly how to solve this. It was definitely a trick. And let's see what it is. I have to find a way to make the base the same. 25 is the same as 100 divided by 4. It's 5 squared. It doesn't really do much for me. There's no exponent of 10 that equals 25. I know there's a way of, I think I know what it is. So if this is true, then this is true. Right? My law of exponents says an exponent of an exponent can be broken down, which means I can square root both sides, right? If I square root this square, it just disappears. But if I square root this, it's 5. Now, there's a little secret here. When you take a square root of an unknown like this, you have to do plus or minus 5, which means 10 to the y is equal to plus 5, or it's equal to minus 5. Okay. If 10 to the y is equal to these, the only thing that minus y would do is change where it goes. So 10 to the minus y would either be minus 1 over 5 or negative 1 over 5. You might ask, why is the square root also negative 5? Because negative 5 squared can get me back to 25. So there's a possible. For instance, when I ask you the square root of 4, it's not 2. It's plus 2, but also it's minus 2. That's because minus 2 squared can get me back to 4, and plus 2 squared can get me back to 4. Your calculator will just always spit out plus 2 and expect you to know the other variation. So here I can see that 10 to the y is equal to 5, and 10 to the y is equal to minus 5. Well, all a minus does is say, okay, we'll take whatever that number was and put it as a fraction, which means 10 to the negative y. Oh, and it says where y is bigger than 0. Yeah, okay, so yeah, I think we can exclude the negative because there's no way I can put a y here that will bring about a negative, which means 10 to the y can be only 1 over 5. Or sorry, 10 to the negative y can only be 1 over 5. So that was the logic of that one. Sorry, I had a little brain fart. Simplify. Okay, so just follow the rules each time. The rule says I have to multiply these fractions, which means it's 2 times 5 and 2 times minus r. So it just becomes x to the, what's 2 times 5? 10. What's 2 times r? Minus 2r. And the reason you would do this is because if suddenly I have it equal to, I don't know, somehow I figure out it's equal to 100 to the same exponent, the only way this can be true is when x is equal to 100. So there might be cases where you'd have to solve it. So you need to learn how to expand it properly. This one is just adding an extra twist to it. It's making you do it a few times. So 3 times 7 is 21. 3 times minus r is that. So you get x to the power of 27 minus 3r. But when I multiply it times x to the r, the rule is I can add those exponents. Oh, x to the r, x to the r. The rule is I can add 27 minus 3r plus r. What's minus 3r plus r? It's minus 2r. Which means the final resolution of this is that. Okay, so we did that and that. So this is a division, so the easiest thing is just to put them underneath one another. And then realize that their exponents can subtract. So I have to do, it helps if you put them in brackets. 2m minus plus 3m minus m minus n. Well, that minus applies to both of them, so I get minus m plus n. And if I look at this, what's 3m minus m? It's 2m. And what's oh yeah, why does it say, that must be a printout. It would be 3m plus 3m because that's 5m. So that must, one of these should have probably been an n up here. And then 2n plus n is 3n. There's no way they would have put 2m plus 3m up here because that's just b to the 5m. There's no need to separate it like that. But anyway, you just resolve it like that, and that's what the new b exponent is. You just follow the same rules. Okay, so what's the rule here? Well, this p simply applies to both things. 1 to any exponent is just going to be 1. So a to the p here. And when you multiply them like this, it's essentially this part multiplies the 1 up top. So it becomes a to the 10 minus p up top divided by a to the p. So you do the same thing. You do 10 minus p up top minus p. It's the rule, so it's minus 2p. So the final answer is a to the power of 10 minus 2p. And it doesn't get simplified any more than that. That's the final answer right there. And this, you have to study your brackets carefully, so you can see that this bracket must be done first. And also be aware that this 6 minus 2m applies to that item and that item. So really, we get a 3 to the 6 minus m, and an x to the 4. What's 4 times 6? 24. What's 4 times minus m? Minus 4m. Then it's multiplied by this m. Well, this m applies to the 1 and then to the x, and 1 to the m is just 1. So this whole thing is multiplying m, or multiplying 1 over x to the m. So essentially this whole thing is this over x to the m. Well, the only thing in common is the x's. So you do 24 minus 4m minus m, which is clearly minus 5m. So the only thing that this resolves out to, you can get rid of the denominator now, and you just change this exponent here to that. There's nothing more you can do after that. There's no more solving it because there's no more information. These last ones aren't as useful actually as the one I just did, the logic one, and these ones up here. 16 and 17 is way more useful than 18. And I'll do 4.3 next time.